after what Christian explained in the fundamentals. And basically our job at Boehringer Ingelheim is to find applications for quantum computing in drug design. So Boehringer Ingelheim is a large multinational pharmaceutical company, and what you read in all news outlets or in grant applications is that quantum computing will sort of revolutionize drug design and will make things much faster. So our leadership was very interested in this technology and hired 5 people, 5 PhDs in physics, to research what was going on and to see where drug design can make a difference in our value chain. So it's a very applied and industrial viewpoint on what quantum computing means. And so first question, of course, is what everybody is after. So the short is like, will quantum computing solve drug design? And I think this question we get a lot, and it's sort of unfair. Like there's no technology or no technological progress that we expect to solve a whole field. So if you say, will quantum computing give me a drug, that question makes absolutely no sense. What do you mean by that? Will you enter the question, give me a drug against liver cancer, or and a quantum computer will give you the answer? That's very unrealistic, and that's just not how science works. So quantum computing is not science fiction. It's very much rooted in science, and we should be applying the current scientific standards in what we expect from quantum computers and in what we do with quantum computers. So for us, this is a totally like irrelevant question. So for us, it's more, what does it mean in drug design to be successful with a quantum computer? So when do we consider that a quantum computer gives us an advantage, and when would we use it in drug design? And that's basically when a quantum computer even contributes the slightest part of knowledge or of information to our decision process in the design of a drug. So if you do a calculation on a quantum computer, it gives you information and you make better decisions or righter decisions with respect to which drugs to keep, where to apply those drugs, how much of the drug to use, or in convincing people that the drug is safe or that you should use it or you shouldn't use it. Then that is sort of where our end game is. It's not in fully designing a drug from nothing to everything on a quantum computer. That, well, never say never, but that will never happen. So for us, it's important to keep these things in mind. And so to manage the expectations, we think that we should start from the strengths of quantum computers. So not expect quantum computers to be, for instance, large language models where you can ask questions. That's just not something the technology is strong at, and not the level of maturity that the technology has. So we think that we should take the strengths that quantum computers do have and exploit those at the maximum. And then for us, it's important that we are very realistic on what we can scale up. So currently there's lots of quantum computing applications in research and in publications that are claiming an impact based on very small examples, but there's no road or no path between what they show and the realistic sort of size that we need in a drug design cycle. So for us, that makes no sense to investigate. So you need to have, if you do a proof of concept, it needs to be scalable to the realistic size. Otherwise, it makes no sense. And that's something we guard very much in our research. And then, of course, we have a very nice upside of being in a company, is that we have lots of domain experts and lots of knowledge in-house in the company of what exactly we need to solve to bring pharmaceutical development further. So for us, it's a nice feature to be able to talk to people in computational chemistry, to have enormous amounts of data about past drugs or about past experiments even that people have done on drug molecules. And so we can use all of that knowledge to maybe not even answer the right questions, but ask the right questions. So I think if we look at the difference between the industrial research and sort of the academic research, is that we are able to discriminate better which questions to ask. And by asking them, we can drive research into a useful direction, a direction that really matters to us. So that was sort of also the goal of establishing a research team in-house inside the company, and not outsourcing this kind of research to other people or other companies. So why does Boehringer Ingelheim, a pharmaceutical company, sort of start a quantum computing lab? So inside a drug discovery cycle, you start with maybe 10,000 molecules that you think that are relevant to the disease and the disease target. And then you do a whole cycle of calculations and experiments, and each time the outcome is that you have less and less and less molecules that are potential targets or potential leads. And this has the shape of a funnel, right? You start with many molecules and you end up with only 5 and eventually 1 drug that you bring to the market. And the real reason why people are interested in speeding this up or making this more accurate is that it's enormously costly. Making a drug is enormously costly. Like doing experiments on them is enormously costly, just in resources, in time for researchers. So just every aspect of it is very costly. So if you can make better decisions, and if you can sort of select better molecules or have more information than you had before, you're saving lots of time and lots of money. It's not only us that stand to benefit, it's also the general public, right? Your drug would be developed faster and you would save lives as well. So, so the outcome of this is that we need more predictive calculations of chemical properties of our molecules to do basically better drug design. So, and that's what we are thinking about quantum computers for. So quantum computers are basically, as Christian explained, are very well controlled quantum systems. So they behave quantum mechanically. So naturally, they're very good at simulating quantum systems. And that's the first 2 things that we think quantum computers will be very good at, is looking at how a quantum system evolves over time. And one special side of that is to look at which state of the quantum system is most stable. That's the ground state. That's the state that a system spends most time in. And it's very important because that also, since it spends most time in its ground state, it's also most relevant for its properties. And then, of course, Christian explained the intro to integer factoring. That's the one algorithm by Shor that stands to break cryptography. Then there's one algorithm by Grover, Lev Grover, that is about unstructured search, which also has a potential speed up, but of a smaller kind. And then there's the matrix inversion algorithm by Lloyd, Hasidim, and Harrow. So yeah, that's the HHL algorithm. So these 5 algorithms, these are fundamental building blocks that we think quantum computers are better at. Of course, since we're a pharmaceutical company, this comes with some sort of prescription. It's not just for any example of these systems. So for instance, for the ground state search, it's very well known that this is a QMA hard problem. So we cannot find the ground state for any Hamiltonian with sub-exponential cost. So there's going to be requirements, there's going to be small print, and to be able to even tell which systems will be able to treat faster, it's an incredibly hard task that even in research people disagree about. So there's fights about which ones of these things will be useful in the end. There's also a dark side, things that we do not think quantum computers are very good at, and that maybe will burst some bubbles. So one of the issues that quantum computers definitely have is that the interface with the classical world, like for instance, entering data and measuring data, is extremely slow. So if you do that, and you need lots of access to data and have large amounts of data in your problems, for instance, training machine learning models, for instance, these large language models, as it stands, this is not a very good application for quantum computers. And then the next thing is also there are things that are, even though quantum computers are able to do anything that a classical computer can do, the translation and sort of the factors of resources that you need to do a classical problem on a quantum computer might not be in your favor. So it will definitely be true, as Christian also explained, that this will be special purpose. Not all things, not all games on your cell phone, not your TikTok app, not all things will be executed on a quantum computer faster and more efficiently. So also there, this is a dangerous prediction. Things in the very far future might not look like the present at all, but as we understand it, that's how we see it. And then, Christian also touched on error correction. So this is a very old, I think 2017 or something graph, but sadly the current state of the art has not progressed beyond it to make it invalid. So currently we're still in the noisy intermediate range quantum computers, right? The NISQ computers, and they are not very useful, as one would say. For instance, the quantum supremacy experiment that Christian showed, it's not a very useful calculation. Like if one would think of calculation as giving you information about something, this was sampling from a distribution coming from a quantum circuit. So it's not really something that solves one of our problems. And that's the one thing we can do faster on the current quantum computers than on classical computers. So we're very much thinking that even though there are unsolved problems, that we will need this error-corrected quantum computers that Christian floated, and that we will need fault tolerance for us to be able to do useful things on a quantum computer. And the algorithms that we design right now are very much for that future. And some people disagree with that. They say, okay, this quantum computer does not exist. Are you even sure you will be able to build it? And yeah, to them, we are very aware that we're taking a risk there by designing things for the very far future. But I invite everyone, like if other people would be able to do something on these near-term quantum computers, of course we would also be happy, and I'll happily be proven wrong. So we currently think that with the noisy quantum computers without error corrections, it's very hard to do anything beyond classical capabilities. So this is a bit of a positioning statement. So if you see the quantum computer, the computer on the left, that's the ENIAC computer, and that's sort of the predecessor of everything you have on your desk right now. And on the right, you see one of the, I would say, more professional quantum computing labs. And you see the analogy, it's very much still an electronics/physics experiment in the lab. And I would say also with the applications, with what we can do with them, we are very much in these early days of computing. The nice thing, I mean, that's the negative, right? That it's very, very early. The nice thing is that we have taken this path before, right? We have evolved the left to what's currently on your desk. So we do hope that we can evolve quantum computers to the state of usefulness faster, since we've already taken a similar path with classical computation. So all that to arrive at a first use case. So now I'll be giving you 3 use cases of things we think you can, or things we have researched to calculate on a quantum computer. And the first use case is simulating molecules. So when people talk about quantum computers, they say, okay, they are behaving like a quantum system. So if you have a quantum system, you must be able to make your quantum computer look like the system, sort of copy its behavior, which is encoded in the Hamiltonian, and extract knowledge about this quantum system that you're interested in from now sort of a simulating quantum system. And for us, that's the systems that we're interested in are molecules. And we're a company that mostly does small molecule drugs. So the sort of way of action of our drugs is that we have these small molecules that approach a large protein that consists of many atoms. They either inhibit or enhance their activity, and since this protein is linked to a certain disease, the disease now stops happening. So what we want to look at mostly now is the ground state energy. So this means this energy of the molecule when it is in its most natural or most relaxed configuration. And what you see here is a cytochrome that is a protein that is situated in the liver. And you see what we normally use on the bottom. Those are technical terms, but those are the methods that we normally use to calculate these energies in the most favorable configuration. And you can see that on the left, you have very large systems and very many atoms, and on the right, you have very few. And on the accuracy also goes up from left to right. So we can treat only very small systems very accurately, and the very large ones we have to have strong approximations which decrease the accuracy of the answer. And for some of these systems, like the cytochrome, one would need the answer at the, for instance, the couple cluster size, but one would need the accuracy that's at the full configuration level, full configuration interaction level. And that's a problem because this couple cluster geometry is way too large for us to be able to get the exact answer and to make accurate predictions. And so since a quantum computer should have or potentially has exponential speed up for finding ground state energies of molecules, we put this forward as a potential calculation that we want to do. So this here you see the the configuration or the geometry of the molecule that we wanted to calculate. And it's important because it's situated in the liver, and each of our drug molecules passes by this cytochrome molecule, and it basically breaks down double oxygen bonds to single oxygen bonds, after which the molecule falls apart more easily and your body gets rid of it. If this pathway would not work, if this chemical reaction would not work, the drug would be in your body basically indefinitely, and that's not good, would make it very toxic. So what we want to do is now put forward a fault-tolerant algorithm, which is basically based on what Christian showed in the Shor's algorithm, which is quantum phase estimation. And the quantum phase estimation is basically using Shor's algorithm for integer factoring to find ground state energies of quantum Hamiltonians. Sadly, if you take this large kind of molecule and you want to get the energy for it, it becomes very expensive. So if you see the number here, you can see that it requires 1400 logical qubits for a system that only has 58 orbitals. And you need 7.8 billion gates. People sometimes forget this, but a current quantum computer for an error-corrected quantum computer, you expect clock speeds of about 1 megahertz. So if you then look at the runtime, this comes down to 3 days. And I don't know if you know how fast people can make a molecule in the lab. That's about 2 days. So here, it makes more sense to basically make this molecule in a lab, do some experiment on it, and get the answer exactly, than doing a digital computation on a quantum computer. So this is maybe a bit of a negative result, but for us, it was more of a signal to orient our research, and people consider this ground state searching solved, or they consider that we're sort of in a good place, right? We can solve, or we can search for ground state energies of molecules. But I would urge people to think more, more in the other way, and say that we definitely need research that improves the speed of this algorithm, that we need to find faster ways to do the thing we already know how to do. Otherwise, it will not be industrially relevant. And that's a bit of a sad thing about a technology that comes once another technology is already mature. You don't only need to provide the first answer, you also need to be faster than anything that is around. And that's sort of a problem, because you also need to compare to experiments. And then you see 2 numbers for qubits, and that's the logical qubits. Those are error-corrected qubits. And then below you see 4 million, and that's the physical qubits. So the qubits that are also responsible for error correction. And then there you see the number 4 million is in the range that Christian also quoted for fault-tolerant algorithms, and it's much higher than what we see on current quantum computers, right? So what's the nice thing is that we analyze the runtime of this algorithm versus the best known classical method that can execute this, and that's the density matrix renormalization group. And you can see that we do think that by executing this algorithm on a real quantum device, taking everything into account, magic state distillation, every part of error correction, that we are able to beat the classical method that maybe is able to provide the answer, maybe not. But the thing you also see is that at the point where the two curves, the green and the blue, are actually crossing, the answer gets less clear, right? Whether one is more favorable or the other. So we would like to have the crossing. So we basically would like to decrease the constant factors of the green curve, the quantum calculation, so that we have a more confident crossing and that we can say for sure that we would beat classical computers currently. And yeah, just a caveat, this is, I think, the one core calculation on the classical computer. So we are skewing the comparison a bit in favor of the quantum computer, but even if you divide the blue curve by 100 or 200, at some point it will cross over. So in that respect, we do think that there will be a speed up for this sort of method. Okay, so the good thing is, so a conclusion of this work is that we do have, if everything fails and we can find nothing else than running quantum systems on a quantum computer, we have a full end-to-end algorithm that we can run if we need to. So this is very nice. We can expect to predict things better than on classical computers, and I think getting accurate energies for transition metal complexes is pretty hard, and people agree that we need better solutions there. What the downside is, of course, I already talked to you about the 3-day of runtime, and that's really too long for us, but we're working on that. And then there's, of course, this is a very special example. So I think currently people have proposed about 5 of these molecules to attack with a quantum computer that have been investigated seriously with constant factor resource estimates. And this is a very restricted set of molecules that you would calculate. And that's just not good enough. Like if we invest billions of dollars in development of quantum computers, and all we can think of when we have them is to calculate P450, FEMOCO, and some ruthenium catalyst, that's just not enough. I mean, we need to be very clear on 2 funding agencies that we know what to do with the quantum computers when they appear, and to have realistic plans with programs written out, with resources costed out. And I think also in the last few years, I mean, 2 or 3 years, people have spent more attention to bringing forward these well costed out examples, but it's still something that's lacking. Lots of the literature and the algorithms are in terms of big O scaling, which is basically saying how something will scale when you just increase the size of the system. But we need specific instances that we will calculate. Maybe I'm too cautious, and it will take so long that none of these numbers are still valid by the time quantum computers become powerful enough to execute them. But I think the iron molybdenum cofactor has been around for 10 years, and it's been a good benchmark and a good sign of progress of speed of quantum algorithms as well. So in that respect, I think it's good to have these examples. And then the last point on the bad side, there's this single energy that I've now talked about is not something that is direct information for us. Most of the time, drugs are at a finite temperature in your body. They wiggle around. They have many configurations in space, many geometries, and this requires many repeated calculations in different geometries of the molecule. And for us to do that and to find primitives that do that, that is sort of the the topic of the next two use cases that I'll present. So what else should we calculate? And there we look mostly into things that we are interested in our company. So what we do on the computational chemistry side is molecular dynamic simulations and binding affinity. So molecular dynamics is basically looking at a time evolution of a drug in the presence of the protein, sort of looking just how things evolve over time. And binding affinity prediction is predicting which of your drugs is most favoring or is most favored to bind to your protein. And that's the next two topics I'll shortly or briefly discuss. So as I said, molecular dynamics, it's looking at a time evolution of your system. And what you do is you calculate your energy at a certain time. You find the gradient of that energy with respect to the positions of the atoms. You move your atoms and you do a next calculation. So to know where the atoms need to go, you need the derivatives of the energy. So there's more than just looking at the time evolution that you can do. So this is used to find the geometry with the most favorable energy. You can also just minimize the energy doing this. By looking at the time evolution, you can use the ergodic principle to find thermodynamic quantities, so finite temperature properties of your molecule using this, this time series of data. And yeah, it can also, yeah, the last thing is just looking at does a molecule stay present with the protein and for how long, and finding data about that. So the problem with finding forces on a quantum computer is that it's not an eigenvalue problem. So finding the force does not come down to something that you can translate directly to an eigenvalue problem or to the Shor algorithm for factoring. And that's sort of a problem because the thing we know very well how to do is this Shor algorithm, and we know that it has a speed up. But for other properties like expectation values, which this is, we don't have such primitives. And so we set out with the Google Quantum AI team to find the most efficient way to find these forces for our systems on a quantum computer. And we basically came up with two solutions. Either you just treat the force as a sum, or in this case, a difference of many energy evaluations. So you keep cranking your handle and keep doing just energy evaluations as before, right? So you keep using Shor's algorithm. And on the other side, you do something else. There you are trying to get an expectation value out of your quantum computer. So this is different from eigenvalue. But the trick is to actually make your expectation value estimation look like an eigenvalue through amplitude estimation. And this is sort of making the thing that is not looking like Shor's algorithm look like Shor's algorithm. Sadly, you pay a big price for that, which is that you need to be able to prepare the ground state coherently. So you need to be able to solve a Shor's algorithm inside a Shor's algorithm, basically. And those are the two most efficient ways that we came up with doing that. And here you see some of these big O scalings that I talked about before. And what it comes down to is that if we do force evaluation on a quantum computer, we can do it, but it is about as expensive as getting an energy. And that would be fine if you could do energies really fast, but it's problematic if you need to move all your atoms, and you need to do it for many, many time steps. So in a typical calculation, we need to do this 10 to the 6 times. So that's 1 million times. And yeah, If you need to do something that costs 3 days, 1 million times, that goes beyond your lifetime. So won't happen. So again, this shows us that even these fundamental algorithms that we think we have sorted and we have very efficient routines for us to use them in industry, they need to be faster. And that's not, again, not a thing we are criticizing people on. That's more something we take as a responsibility to develop and to improve. One reason we thought that maybe this molecular dynamics was not working for was that we are again reading out data from the quantum computer. When you are calculating forces, you are asking the quantum computer, what is this force? And then I move my my atom. But we're really not very much interested in these forces. These forces are just used to move the atoms. So then with the University of Toronto, we devised this method to do the same algorithm, but make the movement of the atoms on the quantum computer. So do this coherently. And this is really something where I think we truly made new things happen. And we really developed a new algorithm to sort of overcome the older shortcomings of our method. And for each of the registers that describe the position and the phase space of the atoms, we coherently do the electronic structure, get a phase kickback, and do the Liouvillean update of the positions coherently. So this is a very technical paper, but we're quite proud of it since it's a very extendable sort of algorithm, where many of the tricks that are used in classical molecular dynamics, we did not necessarily implement them, but they are definitely possible inside this framework. And for us, it was cool to do something that at least would overcome some of the shortcomings of the original algorithm. So please check out the reference that's on the bottom of the slide. So yeah, for us, it was very good to have a signal that you can do MD with a quantum computer. So it's not impossible. It's just very expensive. We've then tried to improve this, and this Liouvillean framework, I think, is a good addition. And it also is filling a gap that we also described in our perspective, which is that we need more routines, basic routines, to be implemented on quantum computers. So we cannot only do ground state search. We need to do expectation value search. We need to do updating of the positions. We need to do many, many things coherently. And if we don't get a speed up, at least we have a larger toolbox that other people can pick out tools from. And the more we are able to perform on a quantum computer, the more chance we are having to find something that is faster. So in our perspective, we do really need to expand the number of things we can do with a quantum computer. Sort of the useful functions for it need to go up. And so that's sort of a second after the useful instances. Now we don't only need the molecules that we will want to calculate, but also the algorithms we will want to execute. And then, of course, the bad side is that there's many caveats to this. For instance, getting the entropic contributions for the free energy is still an exponentially scaling problem. And the constant factors for these things, when you do a QPE inside of a QPE, sort of a Shor's algorithm inside of a Shor's algorithm, you're looking at a very long runtime. And yeah, that's a recurring theme in my talk. And the third use case is about these binding affinities. So what is a binding affinity? It's basically looking at your protein and your molecule and their energy together, and what's the difference with their energy separately. And what you would normally do is calculate their energy together, but if you hear that together, you already think at more atoms, right? So the cost of doing that calculation of these two things together is much larger than just looking at interaction terms. And that's basically what we do in this classical method. So it's called symmetry adapted perturbation theory, where instead of doing subtractive interaction energy calculation, we do it from physical principles, and we calculate the relevant interaction parts without having ever to put the two molecules together. This is one of the things we actually did execute in a very, very small proof of concept on a quantum computer. So this is the device by Alpine Quantum Technologies in Austria, Innsbruck. And this is 4 electrons and 4 orbitals, so it's very tiny. You see the model spaces in the middle. Those colored blobs are isosurfaces of the orbitals, and it resembles very well the predicted spectra or the predicted interaction energies. But for us as a quantum team, even though this is high impact and it got published in a really good journal, what we can calculate is fully on a classical computer, right? You see the orange lines, it's simulation. If you go for these NISQ algorithms, you sort of know what will come out before you execute it. But it's nice to have that agreement. It would have been worse if they didn't agree. So in that respect, it also is a good exercise to see what you need to do to actually compile this down to a true quantum computer and to execute things and to see what is possible today. And it's more disappointing than one would want. And then, of course, as I explained, we do not want to do these things where there's no path to executing them at scale, right? And we also devised this algorithm for expectation value estimation, which this is, but then applied to this very specific operator that calculates the interaction energies. And we executed this for, again, our favorite cytochrome and artemisinin, which is a drug molecule that comes out of Chinese medicine for malaria. The reason is that we cannot use drugs of our own without violating some terms with the FDA. So we use things that are in the public domain to not hurt anybody's feelings. And you see here the two molecules together on the top right, and we calculated the resources we needed to actually get the interaction energy between those two molecules. And you see that it's I think in the total you need 3,000 gates, 3,000 qubits, logical ones, and 10 to the 19 or 10 to the 20 gates. Again, calculate at 1 megahertz, and that takes even longer than ground state energies. Okay, so this shows that there, again, we have another primitive that we can execute. And as always, if things get faster, we directly benefit from it. What it also shows is that it's really, really hard to just beat Shor's algorithm. If you want to put together quantum algorithms in sort of a way that speeds up the algorithm by putting two components together, it's excruciatingly hard. Most of the time, you end up slowing down things by putting things together. And to design algorithms in a way that you gain something by putting things together is extremely hard. And there's maybe, I don't know, 200 people in the world that can do that. And it's for everyone in research, well, everyone in the community, a research topic, how to do this, how to expand the functionality of quantum algorithms. and how to retain this quantum speed up that we so much long for. So with that, I reach my conclusion, and I think we set out on a research journey, and it made something, like, if anything, it made our vision on the landscape much clearer, and we are now better able to say that the things we need to reach industrial advantage are well, in one term, basic research, but I think we need to improve existing algorithms, find new areas of application, tailor the algorithms to specific problems. Like I said in the beginning, we know that some problems are exponentially hard and we will never be able to solve, but that does not hold for specific subclasses. So I think we need to tailor algorithms more, and then hopefully hardware will keep evolving as it does now, and we will at some point be able to test heuristics on real hardware. And I think there's going to be a tremendous explosion of research topics then as well. Talking about a virtual quantum computer is always hard, and once you are able to actually run things become clear. Okay, so all I've talked about is research by our team here, that's here at Boehringer Ingelheim, and thank you for your attention, and please feel free to reach out if you have any questions about research or quantum computing. I might be in a company, but I'm still happy to talk about any of this.